Yeah, in that case, hi. So my name is Nikita, and I'm a PHP core developer. So I'm one of the people who is working on the PHP implementation. And in particular, I'm also doing work in the area of performance. And of course, as you can see, this talk is also going to be about performance optimization. But before I go into the technical stuff, just some general background of where this is coming from. So I think it's no big secret that recently improving performance has been something of a focus in PHP development. So in particular for PHP 7, I think one of the major features, maybe even the major feature, has been improved performance. So for typical web code, something like factor of 2 or something. But the thing is, with PHP 7, we've kind of hit a wall. So all the obvious optimizations have already been implemented. And at this point, it's basically just diminishing returns. So you have to put in a lot of effort to get any kind of positive result. So if you look at the performance between PHP 7.0 and PHP 7.1, there will be very little difference for typical code. So what I'm presenting today is one of the optimization experiments that we ran, but which was ultimately not really successful. So not successful in the sense that it gives us improvements on certain kinds of code, so computationally intensive CPU-bound code, but it does not really benefit typical web applications. But nonetheless, I think the topic is interesting, and I hope you'll also find it interesting to learn a little bit about, yeah, maybe a new perspective about how all of these things work in the background, how the compiler technology works, and how we approach these kind of optimization problems. So the basic idea is this. The way PHP executes code, so here we have PHP code, is first it's compiled into something we call opcodes. And these opcodes are run on a virtual machine. So opcodes are just instructions. So in a way similar to assembly, but instead of running on the CPU, it runs on a virtual machine which is specific to PHP. So in this example, I think even without any kind of deep knowledge, the instruction should be relatively clear. So we have two assignments, two variables A and B. And then we have an additional instruction which adds A and B and writes the result into temporary, so that's the T0, and then echo prints out the temporary. And what we want to do in general is, before we execute these instructions, we want to optimize them. So we want to put in a little bit more effort during compile time, and then transform the code in such a way that we save time during actual execution. That's the general concept. And generally, before we can apply optimizations, we first have to analyze code. So we have to determine some type of property based on which we can optimize. For example, one type of property we can use is type information. And to get this kind of information, we use a special representation of the code, which is called SSA, and which I'll introduce later on. But this is basically the underlying framework behind the things I'll be talking about now. So, we want to optimize instructions. There are a couple of general classes of optimizations we are interested in. The first one is something called specialization. So here is a very simple piece of code. So just C equals A plus B. And this code compiles to two instructions. So the first one is an addition between A and B, and the result is written into a temporary. And then in a separate instruction, this temporary is assigned to the actual variable. And the reason why we have this kind of two-step process is that in PHP, something as simple as an assignment is already a pretty complex operation. So in the basic case, an assignment just destroys the old value in the variable and copies in the new value. But there are also a bunch of special cases, for example, assignments to reference variables, or even more obscure assignments to objects with an overloaded assignment operator, which is actually something that PHP supports, even though thankfully it's not accessible from normal code. But all of these special cases, you have to deal with them. And the idea, what we can do now is, if we know that the old value of C is actually just a simple value, it's actually just an integer or a floating point number or a boolean or something like that. In that case, we don't need any of that complexity. We don't even have to destroy the old value, because if you have an integer, there is nothing to destroy. We can just directly overwrite it. So that's the first optimization we can do. And of course, this relies on knowing the type of the variable C. At this point, what we still have is a generic add instruction. And what I mean by generic is that it works on all kinds of different variable types. So what it will basically do is something like check if the left-hand operand is an integer, then check if the right-hand operand is an integer, then perform an integer addition. Then check if the left-hand side is a floating point number, right-hand side is a floating point number, and perform a float addition. And then cover all the other special cases like additions between arrays, or additions between integers and floats, or floats and integers, and so on. Of course, if we know in advance that, why does this happen automatically? Damn it. I think I have some kind of configuration that automatically yeah, do you know how to disable it? Thanks. Okay. That would have been weird. Okay, where was I? Yeah, so if we, so generally, we're here. We have to check the types first, but if we know at compile time that actually A and B are both integers, we can use a special instruction which directly performs the addition and does not perform type checks. And going one step further, we can also handle another special case like this, because in PHP, if you add two integers, you don't always get an integer as the result. It can also happen that if you have two very large integers, you add them together and the result no longer fits into a 64-bit integer variable, then you get a floating point number instead. So again, if we know in advance that that can't happen, we can use a specialized instruction that saves this kind of overflow check. So this is one general class of optimizations, this kind of specialization based on type information. Then the second class are what I would call just like classical compiler optimizations that you know from languages like C. For example, in this code, basically everything is already known statically, so we know that variable A is a constant 2, variable B is a constant 3, and A times B is a constant 6. So we can just evaluate these values and replace them. And then in the second step, we also see that the variables A and B are actually dead, so they're assigned but never used, so we can drop them as well. So that's dead code elimination. These two optimizations usually occur in conjunction with inlining. So, new example, here we have a division function, which just divides A and B, and also does a division by zero check. And then this function is called with constant arguments, 4 and 2. So what we can do now is we inline the call. So instead of calling a function, we just copy the code of the function into the test function. What we do in that case is, okay, the arguments are now just simple assignments, so we assign variables A and B. Then the returns become an assignment to a variable, so we assign a return value variable, and we insert a goto to the end of the function. And then the last change we make is a little bit technical. So at the end there are unsets, unset A and B. And the reason why that is necessary is that PHP has destructors. And sometimes you can observe them. So if a destructor prints out a message, you can see when it runs. And this basically just makes sure that if that edge case occurs, the destructors still run in the same spot. So, and once we have done the inlining, we can run the other two optimizations. So constant propagation in this case would be able to basically compute all the values here, and would also determine that the if is actually dead code because the condition is always false, because here we have b equals 2 and not 0. So the end result here is something like this. And then the dead code elimination can drop all the remaining code because it doesn't do anything anymore. So that's basically the ideal case of what we want to see. We have a function call, and now we just have a constant. So if this happens, we are saving a lot. Of course, this does not actually happen. That's just the nice theory. And in practice, it never actually works out that way, but I'll talk about that later. So before we apply these optimizations, we first have to perform some analysis. In particular, the specialization needs type information. And of course, in PHP, we don't really have types. I mean, we do have type annotations on function arguments, but that's not really enough because, I mean, it's just the arguments, but you usually have a lot more variables than that. So if you want to have type information, we have to somehow automatically determine it. And how we do it, that is what I'll show now. So before I get to the actual type inference, we first have to introduce some machinery. So in this code sample, we have a single variable, x, and this variable is assigned 3 times with different types. So the most general thing, or most specific thing actually, we can say about this variable for the whole code is that it's either an integer, a floating point number, or a string, which is kind of not very precise. So what we can do instead, we also specify the location. So we say in the first 2 lines, x is actually an integer. Then in the next 2 lines, it's a floating point number. Then next 2 lines, it's a string. And the last 2 lines, it's a floating point number or a string. That's precise, but it's also pretty hard to keep track of information in this form, because usually you don't have a single variable x, you have many variables. And these kind of regions where the variable type is the same will be different for all variables. And trying to keep track of that while changing the code and making sure the information stays correct, that's pretty hard. So what we do instead is we use something called SSA form, static single assignment. And the name already kind of says it. Basically, what this does is instead of having a single variable, we say each time we assign to the variable, we actually assign to a new variable. So instead of having x, we have x1. That's the first assignment. Then the second assignment goes to x2, and the third one goes to x3. Of course, we also have to rewrite the uses. So for example, the if branch writes to x2, so the var dump also has to use x2. And the else branch writes to x3, and the var dump uses x3. The only issue with that is, yeah, basically this case. So here we don't really know what to use, because it could either come from here, so the x2, or it could be x3. That depends on how the control flow goes, whether we go into the if branch or the else branch. And SSA solves this using something called a phi node, which basically just encodes that information. So it says, okay, we have a new variable, x4, and this variable will be x2 if we go in the if branch, or it will be x3 if we go in the else branch. Of course, statically we don't know what will happen, so that's only really decided at runtime, but statically we do know that one of those will be the case. And that's enough to perform this kind of analysis. And if we are in this form, then tracking the type information becomes pretty simple, because now we can just associate it with the variables again. So we say x1 is actually an integer for the entire code, and x2 is a floating point number, again for the whole code, not for just a single location, and same for x3 and x4. And once we have this, the type inference is relatively simple. So here is just a new example, because the other one is a bit too simple for that. So this is again normal code, so we convert it into SSA. So each assignment goes to a new variable. And again, we have to insert a fine note, because the value of x can come either from the loop initialization, or it can come from the end of the loop body. So we have to insert a fine note, because there are two possible incoming values. And now the general concept behind the type inference is this. So we have some types that we know. For example, in this case, we know that x1 is an integer, because we actually assigned an integer literal to it. So it cannot be anything else. And now we just propagate this known type information through all the places where it's used. So in this case, x1 is used in the fine note. So what does a fine note mean? A fine note means, in this case, that the type of x2 will be either the type of x1 or the type of x3. So the type of x1 is an integer, the type of x3 is nothing. So we just assume it's an integer for now. Then we have new type information, so we propagate it again. So x2 is used in the variable for the variable y1. That will be just an integer. And it's used in this addition down here. So here we are adding an integer and a floating point number, and in PHP that gives you a floating point number. So that's the result. And then again, type information changed, so we have to propagate it. The variable y1 is used down here, but this just doesn't matter because it does not assign to anything. So that's a dead end. And x3 is used in the fine note. We already handled the fine note, but because the input type information changed, we have to handle it again. So this time the type will be either x1 or x3. So x1 is an integer, x3 is a floating point number, so the result is int or float. And then again we propagate this, used in these two places, and this is the final result. And the reason why it's the final result is that if we try to propagate anything further, it's actually not going to change anything. So we've reached a fixed point, and if we keep iterating, then nothing changes. And based on some theory, you can show that once this happens, the result is actually correct. Of course, technicalities are always a bit more difficult, because especially, I mean, what you always at least need to know is, for each operation, for example, an addition, you have to know if the inputs are of certain types, what are the possible outputs. And in PHP, this turns out to be relatively unpleasant, I would say, because there are a lot of valid type combinations, and figuring out what exactly happens is a bit tricky, but okay. A larger issue is this. So I already mentioned beforehand that if you add two integers in PHP, the result is not always an integer. So if you add two very large integers, you actually get a floating point number. But for the type inference, that would basically mean every time you do an integer operation, the result type will not be integer, it will be integer or float. And that kind of really reduces the quality of the results. So instead, in addition to the main type inference, we also have to perform value range inference. So we actually have to determine that, okay, the variables a and b are actually small enough that this cannot happen. And the basic idea how the value range inference is done is the same as for the type inference. So we start from known ranges, like single literals, and then we propagate this information forward. Only problem is that PHP only has 8 basic types, so that's a very small type space. On the other hand, the number of possible ranges is practically infinite because, you know, range has a starting point, ending point, and for 64-bit numbers, that's a total of 2 to the 128 possible ranges. And that's basically the reason why doing the value range inference is harder, because if you do it the same way as the type inference, it will actually run forever. Not forever, but for 2 to the 128 steps, which is practically forever. But there are ways to solve it. I just don't want to go over it here. Yeah, so that was what we're doing and the basic idea of how we're doing it. But as I mentioned at the start of the presentation, in the end, this kind of doesn't really work out. At least not for typical PHP code, which is some kind of web application stuff. So there are clearly reasons why it doesn't work, and I just want to go through a couple of them. So there are some very obvious issues, like PHP supports eval or variable variables and other really dynamic stuff like that. So I think I don't have to explain that if a function uses eval, it's really hard to statically determine what it's going to do, so you don't really have a chance there. But that's not really a problem because normal PHP code uses these features super rarely. So if we see a function uses one of those, we just don't optimize it, and because it's so rare, we don't lose anything by doing that. A bigger issue are references. So this example is again for constant propagation. So here we have foobar is constant 42, and we'd like to say that, okay, this is actually just a constant 42. Only problem is we have a function call before that. And this function call kind of ruins things, because this function could be accepting the argument by reference. And if it's accepting it by reference, then it can also modify it, in which case the optimization would no longer be valid. Of course, references are also not super common in PHP. I mean, they're more common than I'd like, but they're not all over the place. So you could also argue, okay, if there is a reference, we just don't optimize it and we're fine. But the problem is that in many cases we don't actually know whether a function accepts by value or by reference. And the reason why we don't know is that if these two functions are defined in separate files, then these files are also compiled independently. So when we're compiling the second file, we don't know anything about the first file. And we also don't know which functions are defined it, which signatures they have, and we don't know whether the argument is by value or by reference. And generally, if we don't know something, we always have to conservatively assume the worst. So we have to assume it does pass by reference and it does modify the argument. And the reason why we have this restriction that all files are handled separately is related to the opcode cache. Because if we don't treat them independently, then we have some kind of dependency. So we would have to track in the opcode cache that file 2, that the compilation of file 2 that is stored in the cache can only be used if file 1 has been loaded beforehand. So we'd have to keep track of these dependencies and make sure they're satisfied, and maybe compile the file multiple times depending on loading order. And that's something we don't do right now. We may want to do it in the future, but it's sort of tricky, and for now we just treat the files independently, and then we have this kind of issue. So that was eval, references, which are kind of the obvious issues. But as usual, the devil is in the details. So there are a couple of more tricky cases which also happen to ruin quite a few things. So A is 1, B is 1, we add them together. What do you think the result is? 2? Yeah, I think usually the answer would be 2. but that's only the case if the file is run directly. So if we run it indirectly, we include it somewhere else, then that's no longer generally the case. And the reason why it's not the case, actually there are quite a few things you can do here. This is just one of them. So we can say that the variable b, which is preserved across the include, so this variable will still be intact when you run the new file. So this variable has a destructor, which means that when we execute this assignment, b equals 1, then the old value inside b is destroyed, and the destructor runs and changes the assignment to b equals 2. So this is one of the ways in which you can make 1 plus 1 equals 3 a reality in PHP. Yeah, and there is really nothing you can do about that. So optimizing code in the pseudomain scope or in the global scope is just a lost cause. There are too many different things that can happen there. There is no chance of keeping track of it. Thankfully, in modern PHP, all the code is inside class methods anyway, so we don't really have that kind of problem. But it's still relevant for legacy code where you usually have everything directly inside files, but okay, I don't care about that so much. So here is another tricky case. Again, we want to do constant propagation. This time not using simple variables, but using object properties. So we say that the object property is 42, and we would like to say, okay, this is actually also 42. Are we allowed to do that? So yeah, between those things there is some kind of code, but this code does not use the object. And in particular, it also does not modify the object. So one would think that it's actually valid. Of course, this is PHP, so not really. So this is a feature of PHP that I discovered relatively late while working on this. It's not very well known, but it really, yeah, you'll see. So an error handler, if you register an error handler, it gets a bunch of information. So the usual stuff is like the error message and line number, file, maybe something like error code or severity, I'm not actually sure. And it also gets a variable scope, which contains all the variables inside the function where the error occurred. So in this case, this error scope will contain all the variables in this function. In particular, it will also include the object, and it's possible to modify the object through that variable scope. So if that commented code here doesn't use the object directly, but could maybe generate a warning, then through the error handler it could still be modified, in which case the optimization becomes invalid. And the big problem is that in PHP practically everything can generate errors. So PHP has something like yeah, maybe 200 instruction types, and 95% of them have some kind of error condition. It's usually something pretty obscure, unlikely to happen, but they're there. And usually it's very hard to show that these error conditions cannot happen. So if it's any kind of non-trivial code between there, we cannot show that. And that basically means that any kind of optimizations on object properties and also on references, which also have the exact same issue, are not really possible. And I mean, I don't care much about references, but for PHP code nowadays, it's object-oriented pretty much everywhere. Everything is full of object properties, and if we can't optimize them, then we lose a lot of potential. Yeah. So that's two of the more tricky cases. that was a bad idea. Okay. So I already mentioned that some of the optimizations I've talked about before, like constant propagation, dead code elimination, they are pretty dependent on inlining. Because usually programmers don't intentionally put dead code into their programs. Usually it only appears due to a combination of inlining and constant propagation and so on. But the thing is, inlining is a very nice concept, and at least in languages like C, it works exceptionally well. So there, basically all the performance improvements start with inlining. But in PHP it doesn't really work out well. So the main limitation we have with inlining is that we can only inline something if we know what is being called. Which is sort of obvious, but it's a rather big restriction because due to the single file limitation coming from opcache, so each file is treated separately, we only know about the functions inside the current file. So we cannot inline something defined in a separate file. So that reduces the scope a lot. Then the second issue is that if you have an instance method call, then a child class could override it. So if it's final or if it's a private, then we know exactly what is being called. But if it's not private or final, then a child class can override it, and what ends up being called may not be the same method that's defined in the current class. We could still inline it, but then it would be speculative. So we would have to introduce a check like, okay, has this method been overridden? In that case, we fall back to the normal code. And if it's not been overridden, then we use the inline variant. But that also introduces complexity, and the additional check might be more expensive than the actual benefit we get from the inlining. And generally, even if we actually can inline something, then it's not always going to be a win, because if we're inlining, what we're doing is we're copying a large amount of instructions from one function into another. So instead of doing a call, which is like 1 or maybe 10 instructions, we're copying a large chunk of code into the current function. And generally speaking, the more code you have, the slower it runs. So that's just due to CPU caching effect. So if you have more code, less of it fits into the CPU cache. So you get more cache misses, which make the code run slower. And finally, so those are the basically performance related issues we have with inlining. But probably the largest thing that prevents us from actually using this in practice is that if you inline something, then your exception backtraces, or backtraces in general, are no longer correct. So in a language like C, people kind of expect that if you enable optimization, then your backtraces may change and your variables are optimized away and so on. But in a high-level language like PHP, there is kind of the expectation that even if you're optimizing, all the usual debugging features are still fully available and correct. It's possible to work around that, store extra information to make sure it's still correct, but that hasn't happened yet. Okay, so that brings us to the results. For results, we can always look at two things. One is micro benchmarks, the other is applications. And usually those behave very differently. So for a lot of performance experiments we have run with PHP, we always see the same picture. So on the micro benchmarks, we get great improvements, like 50% faster, 2 times faster, I don't know. But if you then try it on an actual application like WordPress or something, then you get 0 difference. So that's very common. That's why you should never look at micro-benchmark results. They are practically completely meaningless. So in this case, these are the micro-benchmark. So this is like a standard micro-benchmark suite we use in PHP. And the last column there is the average improvement. So it's, in this case, a speed up of 1.5 on average, so 50% faster, which is okay. It always depends a bit on what the benchmark does. So things like Mandelbrot computation or prime number calculations, they benefit a lot. So this is this kind of typical numerical code which we can really optimize well. While things that work on arrays, that's the middle part here, they don't really benefit, just because we don't apply any array optimizations here. So that part is fine. If we look at the actual libraries, there are also a couple where we have benefits. For example, PHP seclib implements RSA encryption in PHP. So that's again numerical code which does optimize well, so we get something like a 20% improvement there. And similarly, the Iris library implements Huffman coding in PHP, so that's used as part of HTTP2 communication, so the HPAC header packing, if you're familiar. That's where we get 10%. But once we go to the more typical types of PHP code, so not this kind of computational stuff, if you look at something like WordPress or MediaWiki, then the improvement we're seeing is like 1%, 2%, maybe 3%. And if you compare that to the amount of effort that has to go into making this stuff work and work correctly, that's not really worthwhile. Especially because another consideration you always have is if you do these kind of optimizations, you usually get something wrong. So you try to make sure it's correct, but PHP is a pretty complex language with many unpleasant edge cases. So in the end, it always turns out that you forgot something, and then perfectly valid code suddenly behaves differently. So I don't know if anyone has ever experienced this, even with the optimizations we have right now, which does not include some of the stuff I've been talking about here. We already have this problem, so sometimes if you enable opcache, where these optimizations are done, the code suddenly starts behaving differently, which really sucks because people don't expect that. So they don't expect that they have to second guess the implementation and that, I don't know, the behavior in their local development where they don't have opcache is different from what happens in production where they do have it. So that's really tricky issues. Okay, so one of the reasons why benchmarks and real applications are different is that for the micro benchmarks, the type inference works really well, because usually you have something like a single function, maybe 2 functions in one benchmark, and everything is using integers or floating point numbers. So of course we have a relatively good chance of inferring all the types and inferring them perfectly, in which case we can optimize well. For real application, that's usually not the case. So this graph shows how many variables have how many possible types. So PHP only has 8 basic types, if you now ignore custom class types or something. So if you see that a variable has 8 possible types, that means we don't know anything about it. And of course, if we don't know anything about the variable, then we can't optimize it. So on the other side here is a bit of a weird case. So where a variable has no type, that basically means the variable is undefined. And the reason why this number is so high here is just a technicality of the implementation. Because, yeah, when you enter a function, before any of the code is executed, all the variables will be undefined. So at that point, they have no type. So basically, this column can be just ignored. The more interesting part is this one here. So for maybe something like 15% of the variables, we have that they have only a single type. So this is the case where we have perfect knowledge. So we know the precise type, and that is basically the case where we can do some kind of optimization, usually. So 15% is not so much, especially because each of the optimizations only make little difference. So you really have to apply them on a large scale, so it adds up. Okay, so what is the state here? Even though it does not work very well on applications, it does work to some degree on this kind of computational code. So parts of this are part of PHP 7.1, in particular the basic framework, so the SSA implementation, the type inference, those are in PHP 7.1, and also the specialization-based optimizations, mainly because those are especially simple and also especially effective. On the other hand, inlining, constant propagation, dead code elimination, we've decided to not use those for now. In particular because those kind of depend on inlining, and inlining is sort of problematic. Finally, right now Zend is working again on a just-in-time compiler for PHP. So this, just in case you're not familiar, just-in-time compiler means that instead of executing these opcodes on a virtual machine, we first compile them down to machine code and then execute them directly on the CPU. So that's the basic idea. And because this essentially eliminates the overhead of the virtual machine, it's theoretically at least faster. So right now Zend is working again on a just-in-time compiler. It's actually already the third one they're trying. So this one is based on the same SSA type inference framework I've introduced before, and it uses DynASM for code generation. So DynASM is a library coming from Luajit, which is one of the really famous and very, very fast just-in-time compilers. So one of the previous attempts used LLVM instead of DynASM. And one of the big disadvantages of LLVM is that it's really, really slow. I mean, it can optimize code well. So DynASM is basically just code generation, and all the optimization you do, you have to do manually. LLVM also does optimization for you, but it's so slow that this old just-in-time compiler actually took something like 2 minutes on the first request to a WordPress homepage, because it took that long to compile all the code. So this new attempt does not have that particular issue, but unfortunately it does not seem like this is going to work any miracles either. So once again, we have great improvements on micro benchmarks, but for actual applications like WordPress as a standard test case, we get something like 5% improvement right now. So this is still a work in progress. Maybe it's going to change, maybe it's suddenly going to be much faster due to some new insights, but that's how it looks right now. And again, just-in-time compiler is a huge amount of work and also a huge amount of maintenance work, because you actually have to write a lot of assembly. So if we only get 5% from it on typical applications, then it's not really worthwhile. But that's basically the state here. Yeah, last thing I want to mention is that we also have a paper on this topic, which goes into a bit more of the technical parts, how exactly this works. And yeah, that's basically it from my side. I hope I haven't made you overly depressed about the state of... I kind of got the feeling that I've been very negative, but okay. So yeah, thanks for your attention.